And at this point, I think we're ready for our first speaker, who is Bill Rose. He's a professor emeritus of geology from Tech. And lately he's begun geo tours, both here in the city and around the Keweenaw Peninsula. I've been on a couple of them, and I found them fascinating. And this is Bill Rose.
So what I'm going to try to do here is talk about the geological part of this, and I'm really going to avoid archaeology just because I don't know anything about it. Okay? And so what I know about it, I've learned from all you guys. And it's a very interesting part of it because it demonstrates, I think, one of the things that I'm most interested in about the copper country, and that is geoheritage. Because what it shows us is that there is a North American Bronze Age equivalent, which is worldwide significance. And it's not quite the same as the European Bronze Age or the African Bronze Age, but it's still very remarkable, and it demonstrates unique aspects of this area in geoheritage. And that really stems from earth science, or really from the deep earth. And it's a message of a very unique treasure that came from the deep earth for reasons that we don't understand. We're not even close to understanding it. And so that's what I'm going to try to do, and that's really why I call it a geo mystery here. And it's something that scientists won't give up on. You'll see people studying the copper here, not for archaeological reasons, but for planetary reasons. And that's an important issue, I think, for all of us to be aware of, even if you're mostly interested in the archaeological part. And so if you aren't interested in this, this is a good time to leave, because I'm not going to talk about people much. I have if you're interested in these topics, I have a website. It's a vast website. It's the result of 4 years of work, and it's going to be maintained forever by Michigan Tech. And the only thing you need to remember about it are the two words at the top: KEWEENAW Geoheritage. And everything else is there, and this is a growing, evolving thing which centers on places to go outside. And there are hundreds of places to go outside, and this site will show you where they are and tell you why earth scientists think they are important sites and sites of geoeducation and so on. And so that's the whole point of this, but it centers around a new word, that's geoheritage word, which really encapsulates the idea that the earth and earth features influence people's lives. And certainly the theme of this conference is compatible with that idea. We have probably in the whole world a place that has uniquely more geoheritage than almost any place. And that's one of the things to celebrate. But most of the people who live here, they're aware maybe of geoheritage, not as a word, but they're aware of the fact that earth science influences their lives. But they can't really articulate it This is just an aerial view of Isle Royale that shows you some of the unique aspects. I mean, we have incredible geodiversity here, many ways in which earth science influences us. One of them is that this is the site of the largest hotspot really in the history of the earth, a place where volcanism was generated on a scale that is almost unknown other times in earth history. We are also the site of enormous quantities of what we call red bed sandstones. These are the things that filled the great hole of the rift that formed as a result of the hotspot. We are the site of native copper mineralization on a scale that is not known anywhere else on Earth, and copper doesn't occur in that form in general. It occurs as a sulfide. We don't know why this is the case. We are the site of a gigantic thrust fault, which bisects the whole peninsula and which gives us a unique access to an insight into the great earthquakes of the Earth, because the fault is exposed at the surface in actually many places. And it creates a landscape. It uplifted the copper so that it is close enough to the surface that people can find it. Without the fault, that would never have happened. It creates the most interesting landscapes on the peninsula, including all the waterfalls that are significant. And then, in addition to that, we have a beautiful glacial history here. Glacial deposits that are unique and unusual, and which led to the discovery of continental glaciation by scientists like Louis Agassiz. And then we are also the site of the most unusual large lake in the world, because it's located in the middle of a great continent and creates a unique climate and weather conditions day to day, which are completely unusual and illuminating and important. And so there's many things to be learned in this area, which are all encapsulated in the idea of geoheritage. And so that's really what I've been working on, is the interpretive part of this. And Michigan Tech is going to continue this. They've promised to do so, and students are going to continue to update it. So I don't know if there's a way to turn out the lights that are bathing the screen, but that would be a good thing to do if we can. There's lights right up above. That's great. I think that helps. One of the things you should realize about geology that geologists know is that Earth history, in any one place, you don't see all of the history of the Earth. So if we drew a line from the beginning of the Earth to the present, it would look like this, and it would represent 4.5 billion years. And so we have Earth's origin way at the left-hand side and now at the right-hand side. Well, in the KEWEENAW, almost all the rocks that we see, including all the black and the red rocks, are only a narrow part of that time frame where that yellow bar is. About 1.1 billion years old. And we know those ages pretty well because we have radioactive minerals inside the lava flows, which we can date very precisely with radioactive clocks. The glaciers are much younger. And everything else in Earth history is absent here. Either they're buried or they've been eroded away. And so a picture like this would be obtained in other places on Earth too. You can only see little windows of the time. And this is something to remember. Here's some other boxes that show what you might find in the eastern UP, that's EUP, or the central UP. You see some different aged rocks and different kinds of windows. Geologic time is one of the hardest things to communicate to people. People are not used to these big numbers. All the time on Earth when there were fossils with creatures that are larger than the head of a pin, they're all found, in that section from the EUP on up to now. They're relatively recent sorts of features. And so the KEWEENAW record is before all but very simple life forms. Life couldn't crawl out of the ocean in those days because they would be annihilated by ultraviolet radiation. And so it took the work of cyanobacteria over more than half of Earth's history to oxygenate the ocean and the atmosphere. And this process is still going on, but at the time of the KEWEENAW, there was only 1% oxygen in the atmosphere. Now there's 21%. And the gaseous composition of the atmosphere strongly influences the temperature of the Earth. So the Earth had very unstable temperature regimes even after the time of the KEWEENAW rocks. So there's many, many issues going on here. Plate tectonics was starting and occurring. This is just a reiteration of the elements of the local geologic story. And we run field trips that hit these different kinds of themes. And these field trips visit a few of the geosites, but nowhere near the hundreds that are available. So you can explore this, and that's really my goal, and this is to create it. Well, geohistory really begins with items like this, which come from the Milwaukee Public Museum, this particular case. One of my goals, and I hope this organization will consider this as an objective, one of my goals is to have a local museum which could be an interpretive center for materials like these. I mean, they came from here, and we need one. And it's a glaring omission, in my opinion, that nobody offers a home for this. And so when you folks are ready to get rid of your collections, and it's going to happen to you, I can assure you, I'm getting rid of all mine, in preparation for whatever's ahead of me. But I need to know where valuable things go. We need a place where we can look at all these things and understand them and get them interpreted. And we don't have it now. So think about this and consider about whether this could be a goal of an organization like this. Anyway, that's all I'm going to say about artifacts. But the geoheritage that I talk about goes back thousands of years into the time when objects like these harpoons were made. And it's really important that the context of where these were collected and the knowledge that's associated with them gets preserved and that people get to see them. So do something about it. Anyway, what my website really is where to go. Where to go, and these are some of the places we've identified already. We work on both sides of the rift zone, the KEWEENAW and Isle Royale. And you can see I don't have many points once I get out of the KEWEENAW. Here at Michigan Tech for 43 years, I did plenty of local field trips, taking students outside all the time, but usually I came in back and forth the same day. And so that limited what my perspective was. And I was really interested in the volcanic rocks and sedimentary rocks of the rift zone itself and all the wonderful things. So that's what I learned about. And I can tell you all about those places, but you don't even have to ask me. You can just go to the website, and all their locations are located there. Here's an example of a place that might interest you, and which I think you probably all know about, because it comes from the Voyageur legends. That's a copper harbor at the lighthouse, where there's something called the Green Rock Vein, or le Roche Vert. It was what you'd read about in the Voyageur literature. But before that, the Native Americans knew about this place. It's a wonderful vein of chrysocolla, a bright turquoise mineral, which occurs within a vein 4 feet wide, which extends out into Lake Superior from the Copper Harbor Light. And this was written about by people beginning in the 1700s, but it was talked about long before that, and it's part of the legend of this. And so it's a geoheritage location. There are many veins which project outward into the lake, which you can see, and these were the points where people did prospecting and looking for copper initially. The first deposits were vein deposits. And following veins like this chrysocolla vein sometimes were copper-rich veins. And so the first occurrences that were mined were mineral occurrences like this. And you can see the line of the vein, and lots of them were like this. I don't know why this doesn't look good to me, this particular projection, but looks fine on the screen. Anyway, these are locations in Calumet, okay, showing shaft sort of locations and geosites of interest, which is one of the things we're working on now, expanding interpretive signs for key areas within the copper country. And so you'll be seeing more and more information about this. This is a copper vein on Isle Royale in a place called Washington Island. These used to be much more abundant, but as you can imagine, people focused on these and dug them out and took them away. So they're not well preserved, and there's relatively small number of places where you can find occurrences like this. But I think you can imagine at a time in the 1840s that a lot of occurrences like this still existed. The Native Americans didn't find all of them. They found beautiful examples of them, and they dug shafts along them. And so this idea that European mines were found at the same places where initially where Native Americans had already found them is true. But there were also places like this that people have found since, and a lot of these have been dug out as well. And just to show you, the way this looked, these were the initial targets for copper mining occurrences. But what happened with these is that they did something which geologists describe as pinching and swelling. And what that means is that you could dig a shaft along one of these hoping to find copper for a ways, but after a few feet, the copper was gone. Didn't continue along these. And so they were beautiful and dramatic occurrences, and some of the big pieces, like the big piece that has just been unveiled at the Seaman Museum that was at the Quincy Mine, that piece came from Great Sand Bay, and it was part of a vein of copper that stuck up out of the bottom of the lake, and that vein you can still dive along. It's part of the underwater preserve, and it's a beautiful object. They found a piece, Bob Barron found a piece of it which had been knocked over, probably by the glacier, and was lying by the side of the vein, and he was able to harvest it, and that's the piece that's located up there now. So these were the occurrences of copper mines, and that projection of that vein goes uphill to ore deposits that are in the vicinity of the Ashbed Lode, if you know where that is, and near Petherick locations up the hill, the same vein occurrence. There's a picture of it when it was up at the Quincy Mine. And the man below with the bald head is Bob Barron. Okay, and the man in the left is Rick Wunderman, who is at the Smithsonian Institution and one of the people who knows about Ontonagon boulder. The white star that you see on this map shows the location of where that specimen came from, and there's the geologic map north of Great Sand Bay and the mineral occurrence here. I don't know if I have a pointer here or not, but do I? Oh, great. Thanks a lot. Does it work? What am I doing? Oh well. I'm pushing the wrong button maybe. Okay. There we go. So right down here would be the vein that projects. Well, anyway, let's go into the general discussion of the origin of this copper. This is a reconstruction of the plate tectonics 1.1 billion years ago, and it shows something called the Rodinia supercontinent. The history of plate tectonics shows that continents spend time together and then they break apart and go to the corners of the earth, and then they come back together again. So at 1.1 billion years ago was one version of a supercontinent, and this was a really big one. It's called Rodinia. It's sort of a Russian origin, that particular name, but this was a big continent, a big concentration of thick crustal material, which geophysicists say created a giant blanket over the interior of the Earth. The interior of the Earth is full of radioactive elements, which makes it hot because the heat can't escape easily from the interior of the Earth. Rocks have a very poor conductivity, and so it takes a long time for the heat to get out, so it builds up in the interior, and if you put a blanket over it, it gets really hot. And that's what happened to Rodinia. It got really hot. And this area here, which is called Laurentia, and you can see Hudson's Bay drawn on there. Well, there was no Hudson's Bay at that time. It's just done for reference sort of purposes so we can see where we are. And these are all pieces of continents now. And so India at that time was next to East Antarctica. Never mind, you know, the details of this. This has been reconstructed from lots of geological and geophysical observations, and it's very well tested but the details of it are sometimes wrong. And so the general picture is right, but the details may be to some degree wrong. Well, there was a giant rift that developed, and the continent split apart from this blanketed sort of period. And the heat that came out of it was enormous. And, you know, we can draw a picture of what that looks like. And so here we are up here. So you can imagine this, it says North America here. Well, there was no North America then. There was Rodinia then. But a crack formed from about where Kansas is and continuing at least as far as Toledo. Now, geophysicists think it continued on to Alabama. But this crack was centered around a really hot sort of center, which is inside of that circle, and that's what we call a hot spot. There was an enormous outflow of heat actually from the core of the Earth and through the mantle of the Earth up to the surface. And that's geohistory and geoheritage for us, is that we were the site of probably the biggest hot spot ever on Earth because of that huge continent. And it's something to do with that explains the copper. We don't know exactly what, but some of the elements of that were that we had enormous lava flows. Lava flows that created volumes of magma that are surprisingly large compared to anything we know about. So here's a cartoon. You know, you can imagine the outside of the Earth. And here's the core of the Earth and the mantle of the Earth. And the way geologists draw the cartoons of the way things happened, the core got really hot underneath the continent. It heated up the mantle. It created magma bodies that moved up toward the surface of the Earth and eventually came out on the surface. And here's a cartoon from Isle Royale to the KEWEENAW Peninsula showing this zone of black rocks. Those black rocks were 400 gigantic lava flows. And those 400 lava flows had 15 or 18 conglomerate units among them. And then they were covered by red rocks over the surface as the Rift Valley opened and as finally the lava stopped. This was a very short period for flood basalt occurrences to happen, only a couple million years. But during that period were enormous sorts of flood basalt occurrences. This is just an animation done recently by some people at Northwestern about the way the continent split. Just kind of a sequence. First, a crack formed on it. There was slippage along the crack. Then the Rift Valley formed, and the green are the initial volcanic rocks in the sequence. The rift continued to subside, and then sediments came over the surface, and it shows the ages of these and constraint. And you can read more about this if you want to. I'm kind of going quickly through this or we'll never get done, but anyway, an enormous Rift Valley formation. And the present shows rocks on either side of the rift. We had magma oceans. The largest lava flows existed as a magma ocean for about 1,000 years. There's no other way to explain it, but this is something unheard of in recent levels of history. Here's some age dating information. Something called the greenstone flow here, 1,094 million years. As I said, about 1.1 billion years. That's the largest lava flow that we know anywhere on Earth. It's several thousand cubic kilometers. Enough material to cover the entire United States, including Alaska, at a depth of around 8 inches. Well, it didn't cover the whole U.S., but it did fill the whole western part of Lake Superior at least. We actually don't know how much extent it had. So an enormous feature and an outflowing of lava like which the Earth has barely ever seen. Enormous hotspot. There's many things you can read about this. This is a detail from a field guide by Bob Barron and Ted Bornhorst, which you may have seen, which again shows the history of this. And one of the important parts about this is to think about this, where there's a series of dikes that brought magma up toward the surface. There was an enormous heat at the base of this rift zone. And it's really that heat, which took tens of millions of years to dissipate, that was associated with the native copper in some way. It was a heat engine, because the native copper came from hot water solutions, which came upward and altered the volcanic rocks and the sedimentary rocks that were present in the rift zone as it developed. And so the hot spot didn't only drive lava sequences, but it went on for millions of years afterwards and drove hydrothermal hot water situation. Lake Superior itself, the basin of Lake Superior, developed not because of glaciers damming the situation, but really because the basin of the rift was located there. The rift axis makes a turn right along the margins of the lake. And so unlike the other Great Lakes, Lake Superior is really strongly influenced by this old hotspot that happened long ago. And it's the only place along the rift zone where the rocks of that age are exposed at the surface. Everywhere else they're covered up, and the rift is only detected by geophysics, gravity and magnetics, and occasional drill holes which happen. So you could think of the rift axis going, I turn north, upside down here, so you can visualize this, the rift axis. So the rift axis is where the lavas came from, a gigantic fissure that opened along there and filled in the Rift Valley. So the rocks on the Keweenaw side dip toward the north, the rocks on the Isle Royale side dip toward the south, and it makes a rift basin. So otherwise it's a gravity anomaly, and it's been drilled, and this idea has been tested by lots and lots of science, and it holds up. There's very few people who are scientists who don't believe in the rift zone. So we've investigated lots of the features of the lavas. This is an important point if you know Isle Royale, where the large lava flow, the greenstone flow, is best exposed and where you can see it, makes the backbone of the Keweenaw and the backbone of Isle Royale. And Blake Point, you can see the features of the Magma Ocean, and that's where it's known. But you can also see many lava flow features in Houghton. And this starts to get to the story of the origin of the copper deposits. This is right on Montezuma Avenue in Houghton, where you can see the contact between the base of one lava flow, a nice black rock, and then this green bubbly top of the next flow. And so what happened here in the copper mineralization period is that lots and lots of hot water flowed through the porous parts of the rock. And this hot water brought many minerals, many unusual and beautiful minerals, dadolite and epidote and calcite and lamentite And a lot of them were green minerals, so lots of times the lava flow tops are greenish like this, and copper is one of these species. They were deposited, we know the temperatures they were deposited at because we can look at fluid inclusions associated with these minerals, little trapped inclusions inside the mineral species that still harbor the liquid that mineralized them. And so we can reheat them and watch the bubbles disappear and we'll know the temperature. And they mostly form between about 250 and about 320 degrees C. Hot water solutions like we find underneath volcanoes or in areas where there are significant geothermal systems, places where power are generated, California, Italy, El Salvador. Many places on Earth have geothermal power situations. But this is a fossil geothermal system that created the copper, but it must have been enormous. And it was strongly influenced by faulting and fracturing of the rocks, not just by porous flow tops. So here's a cartoon that shows how the fluids might have risen through. These are layers of lava flow features, and you can see how they're influenced by cracks that located here. So the most prolific mineralization periods are near the areas where faulting was the most extensive. So, for example, the Quincy Mine is located right on the Hancock Fault. The Hancock Fault is an offshoot of the KEWEENAW Fault. And there are many sub-features associated with it. There's something called the Holloway Gap Fault. So between the Holloway Gap Fault and the Hancock Fault are the most significant mineralization areas within the district. So fracturing was really important. And there are many, many minerals. You know these if you've grown up here. They're everywhere. These are beach stones, which you can see with many, many colors. And people come from all over the world to find these minerals and to learn about these minerals. And many of them haven't been completely described yet. One example of this is the mineral Mohawkite, which contains significant arsenic. And so we're very interested in arsenic because it's poisonous, and because the arsenic is in many of the mine waste occurrences, and we would like to know more about the mineralogy of this so that we can evaluate the potential hazards of arsenic mobility. Okay, but we're not in a position to do this until the minerals are well known. Mohawkite is not a mineral name. It's actually 9 different mineral phases, 7 of which have never been accurately described. So it's a mineralogical problem that exists out there. This is true of all of earth science, and you should realize this, is that many, many relevant problems are uninvestigated. The earth is too big for the earth scientists to manage it. Okay, we can't tackle every relevant problem. Epidote. In Calumet, mining was sustained because of the existence of something called the CNH Conglomerate. Instead of a vein that might have been 50% copper, the CNH Conglomerate was a conglomerate layer, 25 feet thick, but it was only 2 to 5% copper. Lower grade, but it didn't pinch and swell. And so what they could do is, here's the strike of that bed. So that black line is about 25 feet thick, and it goes right along Mine Street, where the line of shafts is located. And it was mined out. There's a shaded area here. It doesn't show up very well on this, but That's the area that was mined out underneath Calumet. So one of the interesting things that's happened about the CNH Conglomerate, it was mined down to a level of about 10,000 feet below the surface, right down a sloping horizon here. And in talking to people in Calumet, a lot of people in Calumet don't even know that there's a hole under Red Jacket. And so that's a interesting thing that interpretation brings out, but it's the reason why mining was sustained here and why the company could continue activities for decades, is because this layer continued below the surface. And it took decades really to discover that the copper that would form the basis of an industry was in a different kind of deposit than a copper vein. Here's what here. You can see the pieces of conglomerate. This is a fairly fine-grained one. And then you can see green areas of copper that were present. And this is the rock layer that's showing the cross-section. Each of these hatchered areas is a lava flow top. The Calumet and Hecla conglomerate is a conglomerate layer called the number 13 conglomerate. Remember, I told you there was only a dozen or so conglomerates in many of these. Another very productive layer in the Calumet region is the Osceola flow. That's a lava flow top, which was heavily mineralized. And so the Osceola shaft, Osceola number 13, where the Great Fire was located in 1896, that was a flow top. And so you see two lines of shafts going through Calumet, one of them following the CNH conglomerate and one following the Osceola flow, and then a few shafts that are located far to the north where another venture dug very, very deeply to intersect the CNH conglomerate a long way from where it was near the surface. And so that was an interesting development of the history. Eventually they sold those occurrences to CNH. Here are some what are called skulls that come from the museum that shows how the copper would accumulate around big boulders within the conglomerate. And this is due really to solutions, and sometimes the solutions were moving in a particular direction, and so there's more copper on one side of the boulder than on the other side. So we learn about the mechanisms of the hot water deposition that are associated with the occurrence. So this is, there's been a lot of geologic work on mineral deposits up here. The history of geology only goes back to about 1830, but Douglas Houghton was promoted as the Michigan state geologist, and that Michigan needed a geologist. Well, he was practically the first person who studied at a graduate level, in geology. Before that, people didn't do that. They were kind of more general scientists, and geology was in its infancy. And so, but one of the first things that happened is that the U.S. formed an agency called the U.S. Geological Survey, and there were state surveys formed, and they focused on what was going on at the time. And this was the first great mineral mining district in North America. And so it received a lot of focus. This is in the back of the elementary school in Calumet, where the number 3 shaft is located. It goes right behind the school and right along 9th Street down to Millionaire Avenue. And this was a great industrial complex. And you can see some of the industrial buildings behind there. But this is what it looked like. And people forget this, but this was an incredible place for industrial experiments and new phenomena. There was a lot invested in these. You can see locations of shafts, but also many, many industrial buildings. And here's just a reiteration of our fault situation, especially the KEWEENAW Fault I want to call your attention to. The Jacobsville sandstone are the red rocks of the region, and the Portage Lake volcanics are the black rocks. Of course, Calumet is located on the north side of the fault. All of the copper mineralization is on the north side of the fault. But the fault has a lot of influence on secondary features like the Hancock Fault, the CNH Fault, the Holloway Gap Fault, which is up here. And a lot of the mineralization is associated with that. That fracturing really stimulated movement of copper and all the other minerals. And so the heavily mineralized zone extends from Mohawk to Painesdale, really dictated by the position of those subsidiary faults. And here's a map that simplifies some of those faults so you can see the way they go. Really important features. Again, the zone of native copper mineralization. I want to go history. This is a rock that we collected from the Eagle Mine. I don't know if you're all up to date on this, but this is the current copper mining that's happening in the UP north of Marquette. And if you look at this in detail, this is really interesting context for the local district. This is a sulfide body. It's a copper nickel sulfide. It has this blebby character. It's a fascinating rock. We're going to put it in the Dow building so that everybody can see it and touch it. It's remarkable. And so this scaling that I have in there is really for the engineers. It weighs 3.5 tons. It's very, very dense sort of material. Really a treasure from the deep earth. And so it poses the question of why is this body a sulfide when the native copper in our district is all native copper. Well, not all native copper, but predominantly native copper. And this is part of the rift sequence. It has an age that's only slightly older than the copper and the lavas within our region. These are part of the earliest dikes that split Rodinia apart. They were very, very hot dikes, what we call ultramafic, 200 degrees C hotter than the dikes associated with the great lava flows. So when the continent first split, it was split by very, very hot magma that came to the surface, and associated with that hot magma was this sulfide material with blebs in it. These are a kind of mineral deposit which we call a Boise Bay deposit. Boise Bay is in Labrador, and this is a new kind of ore deposit which is guiding exploration in many parts of the world now. This model, but there's beautiful examples of it in the UP, not just the Eagle deposit. And so this is an important clue about the way the interior of the Earth works, and a clue about why sometimes copper, almost all the time I should say, copper is associated with sulfur. And only a few times that we know about, and only one important example, our example here, where it occurs in large amounts as native copper. You don't understand this. Somehow the sulfur may have been bled off of the system. That's what people point to in these early examples. Well, maybe the sulfur was somehow extracted from this hotspot situation by events like this. Or what other explanations occur to people I don't think have been completely iterated. Geologists, you know, are paid to tell stories about things, and they guide exploration without knowing all the things that constrain a situation. We are encouraged to tell people where to drill, mainly because I think nobody can think of somebody else that could maybe be a better choice. So they give us the poetic license to make up a story about things. And we do it all the time, and we get very, very practiced at making up stories. Well, the story of the native copper hasn't been made up yet. People are very hesitant because it seems too far out and not well constrained enough. And we don't like to tell a story that's based only on imagination. There has to be some reality associated with it. And so it escapes us why copper in the copper country occurs without sulfur. Here's some, about storytelling, here's some cartoons where people are coming close to telling a story but not really doing it. So I kind of collected these from some people in the USGS about this. And these are important things. There's been some geophysical discoveries, places like Echo Lake and other evidences of magma bodies underneath the Jacobsville sandstone who might be heat engines associated with the native copper deposits. There are occurrences that are associated with the Duluth Gabbro, which is a great intrusive basaltic center. There are cartoons about what's happening deep inside the earth. And all these things play into stories that people might tell, but we, like I say, we really don't have a story yet. So this is just a kind of a teaser that comes from this. I don't really know which of you, has a geologic background. I'm talking to an audience I'm not sure about, so I hope in a sense I gloss over some things and I might assume you know other things, and so I'm sorry that I'm not hitting all of you. I realize that it wouldn't be likely to do this. To be able to successfully communicate this, there's a lot of details about this. The KEWEENAW Fault is an important part of the story, the geologic story, and we don't really know everything about what caused the KEWEENAW Fault. It's a giant thrust fault, which means that older rocks like the lavas are thrust up and they bend the sandstone underneath. Places like Hungarian Falls or the Natural Wall, or where the sandstones are bent upward by movement along the fault. And there was big arguments among the early geologists about how you could explain these kinds of features. But now we think the KEWEENAW Fault is an analog of those great thrust faults that created things like the Japanese earthquakes and tsunamis. And so people come here to look at the fault because we have the fault at the surface, and you can see the fault right at the surface, whereas in Japan or Sumatra, where these fault events are occurring, the fault is a long way from the surface, and you can't see it. It's underneath the sea. And so, but people want to see what the deformation is like. Anyway, along this fault, 1.1 billion years ago, there was a series of magnitude 8 earthquakes. Okay, maybe hundreds of them over a period of a few million years, which created this upthrust, created much of the bending of the rocks that you see there and a compression, probably a continental collision. And we say probably because that's what causes this now. That's what caused the Japanese earthquakes, was a collision of continental material, plates moving toward each other, subduction. And creation of slippage along this. And so that's an important part of the story, the structural complexity. So we have lavas and red beds. Those are the main rocks that we have here, and they've been contorted. And there's the Jacobsville sandstone, located here, mostly flat lying. We have national parks here. Both Isle Royale and the KEWEENAW Park have the same rocks, so we can interpret the geology together. Why should we care about the fault? Well, it influences landscapes, is a conduit for copper, and it uplifted the copper. So it's a really important part of this. These are all bits and pieces of my website. There's lots of geologic history on it. This man, Henry Schoolcraft, is to me the biggest hero of all of this. He wasn't a geologist per se, but he did a lot of geology. He lived in Sault Ste. Marie. He was closely related by marriage to Native American people, so he was involved in the generation of the Hiawatha poem, because one of his relatives told the Ojibwe legend to the poet who created it. But he also understood the copper deposits better than anyone else, and he made, and that includes Douglas Houghton, and he made many trips and descriptions about this. But there's many other people involved in this, and you can read about all these people. This is my granddaughter, and this is where I end. She's sad about her marshmallow, but I think you must be sad now too, because you must feel like there's a lot unexplained about copper, and you should feel that. I think one of the things that's happened is, although we've had all these historic investigations, they were mostly a long time ago, and because of the decline in mining within this district, this problem that I presented to you about sulfur and native copper and treasures from the deep earth is not investigated enough by modern scientists. And it's going to happen. And that's going to be part of our future here, especially if we explain the problem well to people and make the problem accessible to people. The intellectual people will come, because it's a planetary problem of great interest. And we're not going to become less dependent on treasures from the inside of the earth. We're going to become more dependent. And so the value of understanding this will come into our future. Anyway, thank you for listening.